Hello, my name is James, and today I'm going to be going over some MATLAB Simulink obstacle avoidance for a flight vehicle, in this case a quadrotor, using optical flow and some of the VR source simulation arenas tools in MATLAB and Simulink. So, firstly, what is obstacle avoidance, and what is optical flow for obstacle avoidance? Optical flow is an image processing algorithm that calculates the relative motion of an object, a surface, or two edges between any two consecutive video frames. If you could imagine maybe a car driving forward on a road, a video frame of it captured here at point A to point B, what would be the difference in the relative motion in between those 2 points? That could help you predict the speed, the location, relative to your camera, those sorts of things of an object. It's a pretty common computer vision technique. So for the implementation into MATLAB and Simulink, I have a MATLAB start script here, and I am limited on my video time, so I can't go into too many details about this stuff, but it's basic initialization, locations for things. Future versions, this will change to ballistic path for some of the angular stuff for landing. So moving back over to the model itself, we have 5 main areas, 4 kind of major ones that I'd like to highlight. Moving into the model here, we have a VR source. This is a loaded in world, essentially, of it's a 3D model where this drone will fly from the start point to the end point. First configuring, you can go to the block parameters, set up the world itself here, one of the sampling time from the start script, and then prescribe the different things to it. For this case, it's translation, as it is the translation area, so translation sensor. So, and then for the camera here, we have to configure the camera as bird's eye for the onboard camera, because we need the optical flow to be taking the pictures, essentially, the consecutive image frames, from the front of the UAV. So moving forward to how things are actually processed into this calculation here, we're going to convert the data to a double here from RGB. Moving to the actual optical flow itself, we're using the horn chunk method. We're taking the current frame and the nth frame back. Like I described earlier, if you have frames 1, 2, and 3 represented by these 3 blocks, just hypothetically, frame 3 is our current frame. We're taking frame 2 and frame 3 and going to compare the optical flow between them. And that's because I have the nth frame set to 1. This could be changed and tuned as well. Here the optical flow lines are drawn, input image is created, and then the lines are actually drawn, and then that is exported to the video. So you can see the video viewer here for this video, and then the input image is sent into the state machine area. So the input image is put into this function called the flow differences function here. What this is it's just cutting the screen or the image directly in half and calculating if there is more flow on the left or if there's more flow on the right. It takes the difference of that and it will make a command to steer the direction of least flow. Or in this case, least optical mass, because we want the drone to not hit things. We have the initial condition here, which will play in a little bit later in the state machine to talk about how it actually determines what type of flight mode it's in. The optical steering command is sent out, the rotor rotation is sent out, and then the orientation and position are sent out of the state machine. So in the state machine here, we have, and that's just a term to talk about switching the different types of control. So I love this style of workflow here, and I really like the way it's implemented. So here we have our optical flow algorithm, which we're going to be using for avoiding all of the trees. Here we have a drone landing, or in the future situations, ballistic drop and return to home, different type of algorithm. So with this state machine, we can switch between what type of code we want our drone, or what type of control we want our drone to have. So when the X location is less than the switching limit, or before a target has been identified and we're just moving through the pylons, we can use the optical flow as the control algorithm. When we move to this node here, saying that the absolute value of the helipad location is, we've crossed, we're either inside the helipad location or we've crossed the switching limit, we can move to this drone landing, or like I said, in future ballistic drop control. So very nice just being able to prescribe a set location or a set action in the simulation to switch out what type of control algorithm that it's going to use. So that is very handy for simulating drones that have multiple tasks to run. You could do this with multiple systems or cascade this down, and then you could have different types of control be loaded at different times. So that is very handy. I'm just trying to back out to the main model here. Just go right there. Okay. So from that, gotta zoom around a bit. Okay, from that we get the UAV body rotation translation. We also get the rotor rotation, as we just put out as a 1 from here into the propellers here. And then we get the optical steering command, what is actually seen from the front-facing camera. And then this current position helps the drone determine where it is relative to the helipad, and then also just stop the simulation. Moving into the VR sync block here, I tapped it twice so it didn't want to come up. Okay, so here you can see the UAV moving forward. I wasn't able to show some of the things because I had 2 instances running, but from just this observing UAV position, we can see that the UAV is moving through these pillars or these pylons and not colliding with any of them. There might be some clipping with the actual rotors, as it is just modeling a point mass in the center of the drone. So there is no actual model or 3D mesh for these end pieces. So you might see those clip a little bit. I can run multiple situations here, or multiple simulations showing different things. Here is this X limit that is just kind of drawn right on there. So you can see it switch its control to go right to the landing once it hits after about a half a second of time in this kind of end zone area. I'll run it again with the view from the top. Said earlier, this is not a pre-planned path. If these pylons were to change position, the path of the drone would change as well. And here we're going to see it hit its switching limit for the state machine and change to its other type of control for landing, just like that. Alright, well, I hope you enjoyed this brief video about this demonstration of optical flow and object avoidance in MATLAB and Simulink.